Hey everyone, in this video we're going to walk through the steps to solving a problem using the false position method. This method is very similar to the bisection method. If you're unsure how to use the bisection method, I recommend you check out the video I've linked in the description below. So, let's just briefly talk about what the false position method is used for, and then we can go through the steps of how you can use the false position method to solve a problem. The false position method is a closed method, nonlinear numerical method, just like the bisection method. So, it is a way of finding the roots of a function that is nonlinear. So let's go through the steps of how to use the false position method now. Let's say that we have a function that looks like this. Step 1. We define a region, two x values, for which we know that there is a root present. But how do we know this? Well, our first input of x, which I will call a here, will have either a positive or a negative output. Well, whatever output we receive from that output of input A, we want the output from input B to be the opposite of the output of A. This ensures that our function has crossed the x-axis. One common method for validating this is multiplying the two outputs together, as we need one positive and one negative value. The product of these two outputs will never be greater than 0. Now, step 2 is where we differ slightly from the bisection method. If you recall, in the bisection method, we would find the midpoint of our two root boundaries and see which side of the midpoint contained the root still. Well, this is a very conservative guess. So, do you think there is any way that we could speed up finding our root? Well, what if we draw a line from f of a to f of b, and we take the point where we intersect our x-axis as our new c value? But how do we find this c value? Well, let's remember the equation for a secant line. That is, a line that passes through 2 points is the following. We also know that at our root, y is always going to be 0, as we're on the x-axis. Therefore, we can always find our c value through the following formula. Now, we can apply our output product test. This means that we take the output of input A times the output of input C and see if the product of these two values is less than 0. If so, that ensures that our root is to the left of our midpoint C. If the product of output A and C are positive, then we either have two negative outputs or two positive outputs, and our root is not in this region. So we repeat this process for the right of our root and see if output B times C is equal to or less than 0. Whichever side's product gives you less than 0, you know that your root lies in that direction. Then you just adjust your root boundaries using this new information. So, like we said earlier, if f of a times f of c is negative, then we know that the root lies to the left of our new midpoint c. Therefore, b takes on the value of c, and we move to our next iteration. And that is really it. That is all there is to the false position method. We just continue to cut our input range through drawing a line between our f of a and f of b. Determine which side's output is less than 0, and we repeat this process until we reach an acceptable level of error. And lastly, we can measure the error through the absolute of a minus b, just like we did for the bisection method. Typically, the false position method will allow you to find your roots quicker than the conservative bisection method. The only drawback for this method is the same for all closed numerical methods. That is that we need to ensure our function only has a single root within a given region of interest, and we cannot have more than one root in that area of interest. Hey everyone. In this video, we're going to be working through a problem using the false position method. The problem states to find the root of ln 3x minus 3, using the false position method for 3 iterations. Briefly, the false position method is a closed method, nonlinear numerical method, much like the bisection method that we learned about previously. So, it is a way of finding the roots of a nonlinear function. If you missed a theory video on the false position method, I will leave a link in the description down below for you to check that out. However, let's just briefly talk about the steps here. Let's first pull up our function so that we know what it looks like. Now, our first step in solving a problem using the false position method is defining our interval of interest. Remember, when defining these two boundaries, we need to ensure that there is a single root present between these two boundaries, not 0 or multiple roots as I spoke about in our previous video, as this causes us problems. So, for this problem, I will select the boundaries of 1 and 10, and as you can see, there's only one root within these two boundaries. So, let's call our lower root of 1, a, and our upper root, b. Now, we can do a product test whereby we multiply the output of our two inputs, and if there is a root in between them, we will get a negative value in return. As you can see, this is clearly the case. Therefore, we are now ready to move on to our first iteration. So, all iterations using the false position method will follow this structure. Determine a, b, and their outputs. Use the following formula to find where our secant line crosses the x-axis. Then we will find out where our output of c lies. Multiply that by our lower or upper root boundary outputs, and that will tell us if we need to move to the left or the right of c. Then, in the next iteration, we replace the value of either a or b with this c input value, and through this we close in on our root of interest. So, let's get into iteration 1, which is this diagram here. And as I stated, we solve for c, which works out to 8.43. Now, plugging 8.43 into our function, we get an output of 0.231. Now, graphically here, it is clear that we are going to make this c value our new b value, as this test on the right indicates that we must cross the x-axis at least once between the inputs of 1 and 8.43. Moving on to iteration 2, we can just repeat the process of iteration 1. A is going to remain the same as we do not need to change anything about it. As we said, b is now our past iteration c value. We can now solve for c here, which works out to 7.628. Plugging this into our function, we get an output of 0.13. And again from our root test, we determine that the c value will again become our new upper root boundary and replace b. Lastly, for our third and final iteration, we will continue again with our algorithm. Our a values will remain untouched, and this iteration's b values are just our past c values. Now, solving for our new c, we get 7.202, which into our function equals 0.073, which again will push our upper root boundary b to the left. There we go, we just completed 3 iterations of the false position method by hand. Hey everyone, in this video we're going to be walking through and solving a problem using the false position method in Python. We're going to set this up as a Python function, as this will give us some flexibility to use this code again in the future for any function that we want. In terms of the theory behind the false position method, I will leave a link in the description below if you are not sure of the steps that we take when solving this false position method problem. So, let's get right into this. To define our function, we need to type def and then give it a name. So, let's just call it fp method for the false position method. Then we are going to give it 4 parameters. So, our user will need to give us 4 arguments to satisfy these parameters. Let's first ask for their function, func, and the user will input this as a string. Then we need to define the bounds across which our user suspects or knows that there is a root present. So, we add our lower root boundary, which we will call a, and our upper root boundary, which we will call b. Then we need to know the user's acceptable level of error. When we hit this level of error, we can stop our program. To interpret the string that our user entered as a usable mathematical function, we need to create another function that will evaluate our function for a given input, and this can be done like so. This eval method is what we can use to turn our user's entered string function to something that Python can read as a proper mathematical function. Next, we can initialize our iteration tracker, an initial placeholder value of c, and an error term to ensure that our user's current level of error is not smaller than their acceptable amount of error. The iteration tracker will be used to track the number of iterations that it takes to achieve our desired level of error. We must also initialize our c value by calculating the secant line between f of a, our lower root, and our upper root, f of b. Then we can find the error at our initial iteration by taking the absolute error of c minus our placeholder c. Now, we are ready to get into the main looping of the false position method. Let's say that while our error is greater than our acceptable amount of error, we proceed within this loop. Therefore, anytime our error term drops below the acceptable amount of error, our loop will stop and our user will receive their answer. Every loop, we must recalculate the c. Therefore, I'll call this C after, which is the secant line between f of b and f of a. Then we begin an if statement. So, if f of a times f of b is less than or equal to 0, we know that we either have more than one root present or no roots present, and in both situations, the false position method is not helpful. Therefore, we tell the user the problem and quit our false position method function. However, if f of a times f of c is less than 0, we know that we need to move in that direction. Therefore, b takes on the newest value of c. Then we just need to update our current level of error. Without this step, Python wouldn't know when to stop the while looping, so this is very important. We must also increase our iteration counter. Like we just did for our lower root boundary a, we must repeat the same thing but for our upper root boundary b. So let's just copy and paste that last elif statement and then just change our a's to b's. Just in case, let's add a final else statement that will quit our program if something else wrong occurs. Lastly, all we have to do is print the results to our user. I'm going to do this in 3 separate lines like so, but you can present this information to your user any way you want. So, we just have one final step before we enter a few examples and prove to you that this code actually works. We need to enter in a bit of documentation about our code that we created so that a user can quickly know what the function is for and what arguments they need to give it to make it work. Up here, we can just add 3 quotation marks and PyCharm will autofill our parameters. Let's just take a minute and give a short description of the program at the top here and explain what all the arguments that we need are. Lastly, we just tell the user what the output of the function will be. So it will be our newly found upper and lower root boundaries and the level of error. To call the function that we just created, we type the function name, so fp method, enter our function of interest as a string, enter initial, lower, and upper root boundaries, and then an acceptable level of error. Then, when we run our program, we receive the following information, and this validates that the false position method worked correctly here. We could also alter our function and try another one like this. And as long as there is only one root in between your 2 specified root boundaries, then you should have no problem with this code. So there we go, we've just implemented the false position method into Python. Although this may not be the most efficient possible way to code the false position method, I hope it helped and maybe taught you something along the way. In this video, we're going to walk through solving a problem using the false position method in Microsoft Excel. So our problem states to find the root of the following function using the false position method to an error level of 0.05. Our function here is 4x squared plus 3x minus 3. Just as a quick note, if you missed our previous video on the theory behind the false position method, I will leave a link in the description below for you to check that out first. Just remember that the false position method is used to find the roots of nonlinear equations. So, to begin, let's create some headers for our table. Let's just assume that A is going to be our lower boundary input, and B is going to be our higher boundary input. C is going to be our new value, that is our new step, and we'll talk about that in a little bit. But it is found based off our A and B values. F of A, F of B, and F of C will just be the outputs of our function at these specific inputs. Next, we need a column that determines which of the 2 outputs, F of A times F of C, or F of B times F of C, gives a negative value, and this will tell us which direction we need to move, whether left or right. Then lastly, we need to calculate the error at any given iteration. And for the false position method, this can be done using ci plus 1, so our current iteration plus 1, minus our current iteration of c. And that'll make sense here shortly. Now, for this first iteration, we need to assign a and b values based on what we found in our positive or negative product test that we performed in the previous iteration. To accomplish this, we're going to use a simple if statement. So, to do so, we type equals if, and then a logical statement, so that means something that will either be true or false. So, we select the value given by f of a times f of c, and test if this is less than 0. If true, then that means our root is to the left of c, and a will remain unchanged, whereas b will take on the c value. If false, then the root is to the right of c, and a will take on c's value. We repeat the same formula for our higher root boundary b. Now, we are free to bring down all other rows. Every time we create a new row like this, we are basically iterating another step, much like we did in the previous video by hand. Except this method, using Excel, is much faster. As you can see here, after only a few iterations, our error term is already lower than our acceptable value, which means that we are done. And another thing to note is that with the bisection method, solving for the root of this function took us 5 iterations, whereas here it is less than that. And this is usually consistent with the false position method. It is often much quicker than the bisection method. We could also visually depict our function and the boundaries in the following way. Let's create small steps in the x direction. Let's say 0.01, and we go from our initial bounds of 0 to 1. Then, beside this, we can apply these inputs to our function and get the outputs. Next, we can graph the function and visually see that we do indeed have a root between these 2 points, 0 and 1. Next, let's just create a line in our graph and show where our current iteration of the false position method places us in relation to the root. And there you go, we have just completed a problem using the false position method in Microsoft Excel. One additional thing that is cool to add is a validation that we do have a root within our 2 boundaries. So to accomplish this, let's create an if-or statement, which states that if f of a times f of c, or f of b times f of c, and just note the syntax here, is less than 0, we print true. There is at least one root present, and if it is false, we print that. The only times this could give you trouble is if you have more than one root present within your boundaries, and you can ensure that doesn't happen simply by graphing the function like we just previously did. So, just as a final note, you can really use this Excel sheet you just created to solve for any function that you want to solve using the false position method. All you need to do is adjust the formula here for f of a and copy and paste that into f of b, f of c, and f of x for iteration 0 and 1 here. Copy and pasting here works as in this formula our input term is always just to the left of the cell that we are solving for, which is the output for that given input. Then, lastly, you just adjust your boundaries a and b to contain a single root within them. This may take some adjusting, but can easily be done through plotting the function like we did earlier. Hey everyone, in this video we're going to walk through solving a problem using the false position method in Google Sheets. So, our problem states to find the rightmost root of the following function using the false position method to an error level of 0.05. Our function here is 4x squared plus 3x minus 3. Just a quick note, if you missed our previous video on the theory behind the false position method, I will leave a link in the description below for you to check out first. Just remember that the false position method is used for finding the roots of a nonlinear equation. So, to begin, let's just create some headers for our table. So, let's assume that a is going to be our lower boundary input value and b is going to be our higher boundary input value. C is going to be somewhere in the middle of these two values, and it is based off our a and b values. F of a, f of b, and f of c will be found using the function's roots that we are solving for. Next, we need a column that determines which of the two inputs, f of a times f of c and f of b times f of c, gives a negative value. This will tell us in which direction we need to move, whether that be left or right. Then lastly, we need to calculate the error at any given iteration, which is the absolute of our c at our next iteration minus our c at our current iteration. Now, for this first iteration, we need to assign a and b values based on what we found in our positive or negative product test that we performed in the previous iteration. To accomplish this, we are going to use a simple if statement. So to do so, we type equals if and then a logical statement. So that means something that will either be true or false. So we select the value given by f of a times f of c and test if that is less than 0. If true, that means our root is to the left of our midpoint, and a will remain unchanged, whereas b will take on the midpoint's value. If false, the root is to the right of the midpoint, and a will take on the midpoint c's value. We will repeat the same formula for our higher root boundary b. Now, we are free to bring down all of the rows. Just note that every time we create a new row like this, we're basically iterating another step, much like we did in the previous video, except this method, using Google Sheets, is much faster. As you can see, after a few iterations, our error term is lower than our acceptable value, which means that we are done. We could also depict our function and boundaries in the following way. Create small steps in the x direction, let's say 0.01, and we will go from our initial bounds of 0 to 1. Then, beside this, we can apply the inputs to our function and get the outputs. Next, we can graph the function and visually see that we do indeed have a root between these 2 points, 0 and 1. Next, let's just create a line in our graph to show where our current iteration of the false position method places us in relation to our root. And there you go. We have just completed a problem using the false position method in Google Sheets. One additional thing that is cool to add is a validation that we indeed do have a root between two boundaries. So to accomplish this, let's create an if-or statement that states if f of a times f of c or f of b times f of c, and just note the syntax here, is less than 0, we print true. There is at least one root present. Or if it is false, we print that. The only time this could give us trouble is if you have more than one root present within your boundaries, and you can ensure this doesn't happen by simply graphing the function like we just did. Just as a final note here, you can really use this Google Sheets that you just created to solve for any function you want. All you need to do is adjust the formula here for f of a, copy and paste that into f of b and f of c, and f of x for iteration 0 and 1 here. Copy and pasting works here well, as our input term is always directly to the left of our cell that we are solving for, which is the output for that given input. Then, lastly, you just adjust your boundaries a and b to contain a single root within them. This may take some adjusting, but can easily be done through plotting the function like we did here on the right. Thank you for checking out this video, and I hope it helped your understanding of how we find the root of a nonlinear equation using the false position method in Google Sheets. If you enjoyed, please like, subscribe, and consider checking out our YouTube memberships by clicking the join button down below or our Patreon page to support the channel. However, if you have any comments, questions, or concerns about the information I provided in this video, please leave a comment down below and I will do my best to address your concerns.